We know the slope is -10 is the slope of this, because the slope of the velocity time graph is acceleration, and we've established that now twice experimentally. So you should be able to confirm that. So we need to label a couple of things. We're going to just pick a time because we're really aiming for a general form here. We're going to say, look, just sometime, at some point out there, we should be able to get this relationship. So we need to identify some stuff. This velocity here is our initial velocity, the original velocity of the object that was launched. So in this case it would be 2, but we're going to say general and just call it VO. This velocity here we're going to go ahead and call VF, because it is the velocity later. It is the second velocity at this time. Alright, so we're interested in the displacement from 0 to t seconds. So we can fill this stuff. We know the areas anyway. We have this rectangle and we have this triangle. So the displacement is equal to the area of the rectangle, which is VFT, plus the area of this triangle, which is 1/2 the base times the height, which is VO minus VF. So here we have the area of this rectangle. This just doesn't do us a whole lot of good because it's not in the correct form. We need to get some other stuff in here. We need to get some A's, and we need to figure out what this K is. So we need to do some substitutions. Namely, we need to get rid of VF, potentially. VO is a constant in this. It's at the beginning. It's sort of hard to get rid of that one, but VF we can actually rewrite because this is a line. VF is equal to A T plus VO from the equation of this line. The slope is A times the T plus the initial velocity. So we can substitute in everywhere we have a VF, we can put in this instead. So we find that delta X is equal to A T plus VO times T plus 1/2 T times VO minus, we got to be careful with our quantities here, AT plus VO. That's this is inside of the parentheses, so this negative has to distribute. Cleaning this up a little bit, distributing through, this becomes AT squared. Well, that's good. We need an AT squared plus VOT plus, I'm going to leave this 1/2 T for a second and clean these parentheses up, times, we have VO minus AT, distributing the negative minus VO. Conveniently, this VO and that VO, we have plus VO here, minus VO there, they cancel out. Displacement AT squared plus VOT, and all that's left here is a negative 1/2 AT squared. Here's a 1 AT squared, here's a negative 1/2 AT squared. That simplifies down to 1/2 AT squared plus VOT, which miraculously matches this form identically. So according to our velocity time graph, the displacement at any point, as long as the acceleration is constant, should be 1/2 AT squared plus VOT. Comparing that to what we already know our equation to be, it's something t squared plus something else t, and we confirm, yes, in fact, the first thing is 1/2 a, and the second thing is the initial velocity. So we can now go and say, all right, well, let's look at this chart. Okay, so we have this chart. What is the deal with this thing? Well, we knew it's a parabola. So the vertical position is something t squared plus something else t plus what we know to be the initial vertical position. That's at time 0, the position is 0. Well, we know that goes to 0, so that's not a big deal. But we can now write and say from the velocity time graph, we can find that the vertical position is 1/2 AT squared plus the initial velocity times time. Bearing in mind this is actually a displacement. In this case, our position is equal to the displacement because our initial velocity was 0. So that is what you do. Since we can't linearize this thing, we had to go get the equation somewhere else, and that is where you go to get it.